All right, then. I want to welcome everybody here. Thank you for joining today's Research Radar webinar, Traffic and Safety, hosted by the Minnesota Department of Transportation and the Minnesota Local Road Research Board. My name is Julie Swiler. We're excited to have our presenters, Max Moreland, Imran Haye, and Hannah Pritchard joining us today. Today's webinar is the seventh in our Research Radar series, sponsored by MnDOT's Office of Research and Innovation and the Local Road Research Board. Each month, we highlight research projects focused on a common theme. Before we get started, I'm going to read the Tennyson warning. This session will be recorded for those who cannot attend. If you have enabled your camera during the session, the recording may include your image, which is private data under the Minnesota Data Government Practices Act. You are not required to allow MnDOT to use your image, and there are no consequences for declining to do so. To opt out of the recording, simply turn off your camera. MnDOT's Office of Research and Innovation manages more than 185 research projects in progress, ranging from local initiatives to pooled from projects with other states, comprising both basic and applied research. We're here to help transportation practitioners determine whether new research is needed or if existing studies may solve your needs, recommend the best research methodology for your project, access local and national funding sources, and manage your project from start to finish. The Local Road Research Board is a city and county-run organization that sponsors research and educational initiatives that address local transportation needs. You can stay up to date with our research by following us online and subscribing to our newsletters. We will send you website and subscription links in a follow-up email after the webinar. We funded 27 new academic research projects in FY 2025, selected from a competitive pool of 82 proposals. To see a list of all these projects, you can scan this QR code on the screen. And if you have subject matter expertise on any of these projects and are interested in serving on a technical advisory panel, please reach out to our office. Now I'd like to introduce our presenters. Max Moreland is a traffic safety crash data engineer. He has been working in the safety section of MnDOT's Office of Transportation Engineering since 2020. In that role, he works with speed data, crash data, and safety evaluations. Max has 15 years of experience doing traffic engineering and data work. Dr. Imran Haye has been a professor of electrical and computer engineering at the University of Minnesota Duluth since 2024. His research interests are in the areas of communication, signal processing, and intelligent transportation systems. He has published more than 70 publications and holds 18 U.S. patents. Hannah Pritchard is an engineer in MnDOT's Office of Transit and Active Transportation. She works with MnDOT districts around the state on pedestrian and bicycle-related issues. She lives in Minneapolis with her husband and her 3 cats. I'm now going to turn it over to Max to start the program.
All right, thanks, Julie. Let me just get that shared real quick. All right, good morning, everyone. My name is Max Moreland. I'm with MnDOT in our Office of Traffic Engineering in our safety section. I'm going to be talking about a recent evaluation we did looking at the traffic safety of J-turns in Minnesota. So we published a report last year. You can go to the MnDOT digital library, item 202405, or just Google MnDOT J-turn evaluation if you want to find the full report and check into that after I give you the highlights here. So we have over 100 J-turns on trunk highways throughout the state of Minnesota. The first ones went in over a decade ago. We've been putting in a good number each year. So You can see the locations of J-turns here. You've likely driven through one of these in the past, whether you were aware of it or not. On the main line, you might not even notice you've driven through a J-turn. So they're kind of spread out all throughout the state. And the J-turn is a type of intersection that's typically on higher speed rural divided roadways. So you can see a before-after picture here of a expressway intersection. The kind of conventional intersection was a through stop. So side street had stop signs, main line goes through, wide median here. Whereas with the J-turn, the median here is converted into left, channelized left turns, and vehicles on the side street can no longer go straight through or make a left turn. If you're a vehicle on the side street, you want to go through or left, you've got to take a right, come down, make a U-turn, and then come back around again. Of course, I need a laser pointer. Laser pointers are cool. So if you turn your head to the left, it looks kind of like a J. So hence the J turn. If you want to make a turn, you kind of got to make a J movement to get through this intersection. At conventional through stop intersections on expressways, what we're often seeing is there'd be angle crashes. And a lot of times the angle crashes will happen on the far side of the intersection. So if you're, let's say north is up here, if you're on the south leg here and you want to go north and go through, or north and make a left, you've got to judge gaps in two directions of high-speed traffic that have a large physical distance in between them. So what we would often see is a vehicle on the minor road, they'd correctly judge the gap from their left, they'd get across, but the amount of time it takes for them to get across and then how fast these vehicles are going, we would see mistakes in judgment, poor gap selection, and we'd see an angle crash on the far side here. There's also kind of the messy middle of these expressway intersections where some folks will kind of park here, or not park here, will stop and wait here to make a two-stage crossing, but then there's other vehicles coming to turn here, and things get a little chaotic at these intersections. So at the J-turn, it kind of cleans up the middle. If you want to go through or left, again, you got to make a right and then a U-turn. At a J-turn, you're dealing with just one direction of mainline traffic at a time. So you look to your left here, wait for that gap, then you can cross over into the U-turn, turn lane there, come over here, and then deal with the other direction of mainline traffic. So really only one direction of mainline traffic at a time. That's I guess the key to success here is to reduce those severe angle crashes, simplifying the decision making for drivers. And so we have over 100 of these now on our system. So we looked at a number of these J-turn locations, and we looked at the crashes that are happening at these locations. We looked at crashes before they were J-turns, when they were kind of conventional intersections, and then after they became J-turns to see how have crashes changed over time. And then we also looked at intersections that have not become J-turns, and we looked at the crashes at those as well as a comparison. And here's the results. So for different crash categories, we have the change in crashes with a J-turn added, the change in crash rates at the control intersections, and then noting if it was the difference between the two is statistically significant. So for fatal and serious injury crashes where someone is killed or seriously injured, we saw a 67% reduction in the crash rate after the J-turns went in compared to the same amount of time before the J-turns went in. And if we looked at those same time periods at the control intersections, there was no change in fatal and serious injury crashes. So huge reduction in severe crashes at the J-turns. Similarly, a big reduction in all injury crashes. So KABC, that's injury severity, fatal injury, serious injury, minor injury, and possible injury crashes. Over half reduction, over 50% reduction when you put those J-turns in. Angle crashes, which is kind of the target crash type for J-turns, again, 2/3 reduction after we put the J-turns in. And then fatal and serious injury angle crashes. So those angle crashes, T-bone 90-degree style crashes where someone is killed or seriously injured, drop by almost 90% when we put the J-turns in. And the controls actually went up a little bit during that time period. So these are statistically significant differences. It does show that J-turns are very effective at reducing those severe crashes, which is kind of our goal in traffic safety. We're not going to get rid of every crash on the system, but we want to try and get rid of those severe crashes. One interesting finding is we did see rear end crashes did go up at J-turn intersections after we put them in, and I'll talk about that in a minute. And then total crashes dropped as well at the J-turns more than the control intersections, but not statistically significantly more. So we are seeing a reduction in total crashes a bit, but mainly a huge reduction in those severe crashes. So I'm going to dive into these results a little bit more in detail here. So rear end crashes, as I mentioned, did go up when we put the J-turns in. Where are those happening? So I've got two beautifully drawn images here. On the left is before the J-turn went in when the intersection was still kind of that conventional three-stop intersection, and then after the J-turns went in. So looking at the same number of years before and after from our sites that we had. In the before period, vehicles turning right onto the main line and then being rear-ended, that happened 5 times. In the after period, that jumps to 31 times. So again, everyone on the minor road has to make a right turn at a J-turn, so there's just more volume making that turn. It could be slight channelization. Maybe people are going without sufficient gaps, but we are seeing an increase in rear ends when people make those right turns onto the main line. And then on the minor road, where maybe there's more than one vehicle on the minor road waiting to get onto mainline or to cross through, we were seeing rear end crashes there in the before period, 33 of those. That jumped to 93 after the J-turns were installed. These are all low severity, low speed crashes. So no one's getting killed in these types of crashes, but they are increasing. So more of a nuisance style crash, not a dire safety concern, but we are seeing more crashes of that nature. Angle crashes, I said we had 2/3 reduction in the crash rates for angle crashes after the J-turns were installed, which means we still do have some angle crashes happening on the network. So again, on the left is the before period. Vehicles turning right onto the main line, we had 5 angle crashes of that nature, and that jumps to 27. So similar to the rear ends, more crashes resulting in vehicles turning onto mainline, making a right turn, because again, everyone has to make a right turn now. There's no other option. And about half of these are vehicles trying to get to the U-turn, half are just turning onto mainline. So seeing an increase in crashes there. Mainline left turn crashes, so this is where vehicles are turning off of the main line onto the minor road and getting hit by an oncoming vehicle. That actually increased as well, 31 to 37. Not a huge increase, but it is a concerning note that those are ticking up when vehicles are turning left off the main line. It's happening at a variety of locations. It's not clearly obvious that one thing is causing it. It could be due to the channelization. Maybe if the channelization is pretty harsh or a hard angle there, vehicles now have to kind of look to their right as they're making that left turn. So there could be a number of reasons why we're seeing an increase here. One option we have is to not include the mainline left turns here when you're making a J-turn. If people want to turn left off the main line, they can go downstream, use that U-turn, and then turn right. So if you don't need the mainline lefts, if you don't have really high volume demands for these minor roads, and if you can get consensus that you don't need them, I'd say don't put them in your J-turns, because we are seeing crashes there. The other place where we're seeing angle crashes, or I guess a decrease in angle crashes, is, again, those minor road vehicles attempting a through or a left. In the before period, we saw 228 of those angle crashes where they'd get hit either on the near side or more commonly on the far side. And that dropped to 5. This should be a 0 because you're not supposed to make a through or a left at a J-turn, but again, some people try to flout the rules there, and we have had a few crashes where people are getting hit. But again, 228 angle crashes down to 5 angle crashes. That's the big takeaway from this evaluation, is those types of angle crashes are nearly eliminated where they were very common before. So if you want to put in a J-turn, if you have a rural through-stop expressway intersection and you want to change it, your main options are you put in a J-turn, you could put in an interchange, or you could put in a signal at these locations. So we wanted to compare, how do J-turns compare to interchanges and signals at these types of locations? So we looked at the J-turn locations we had evaluated. We also looked at low volume interchanges. So interchanges where the daily entering volume is 40,000 vehicles or less, which is similar to what we're seeing at our J-turns, 40,000 or less vehicles a day traveling through that intersection. So you could build an interchange, which has ramps, has a bridge, has 2 terminal intersections, typically. And what we're seeing is that J-turns actually have lower crash rates than those interchanges. So if we compare total crash rates, J-turns have lower total crash rates. They have lower all injury crash rates, and then lower fatal, serious, and minor injury crash rates as well compared to interchanges. Oftentimes we think of interchange as kind of the gold standard for safety, but it doesn't necessarily seem to be the case in these locations where we can put in a J-turn. J-turns are also a lot less expensive than an interchange. You can put a bunch of J-turns in for the same price as one interchange. So something to keep in mind is they are working pretty well out there compared to the more expensive option. If we look at rural signals, again, you could put in a signal at one of these intersections. J-turns, we're seeing lower injury crash rates, lower angle crash rates, and lower rear end crash rates. Even though the J-turns had an increase in rear end crashes, signals have a lot more rear end crashes, and the signals have a higher angle crash rate as well, which is what we're trying to eliminate with the J-turns. We did a bunch of other, I guess, call them mini analyses for J-turns. You can read about some of those in the report. Two of them I want to highlight. One is the mainline ADT. So we've been putting J-turns on roads that have ADTs as low as just a few thousand mainline, all the way up to about 40,000 vehicles a day on the main line where J-turns are located. We want to see how are they operate, or how are they performing from a safety perspective based on what the mainline ADT range is. So whether mainline's low, medium, or high relative here, we looked at the reduction in crashes. So all of them are showing good reductions in angle crashes, good reductions in the most fatal and serious injury angle crashes. But roads that have mainline ADTs of less than 10,000, we're seeing the best results from. So big reductions in angle crashes, huge reductions in fatal and serious injury angle crashes on those low volume roads. So J-turns are working well everywhere, even on those higher volume roads, but they're working exceedingly well on lower volume mainline roads. And the last thing I'm going to share is commercial vehicles. We looked at crash rates involving commercial vehicles at J-turns. What did we see? We did see an increase. Total crashes did go up. It was not a statistically significant increase. The numbers aren't huge. Again, we're talking over 50 sites over a number of years. So crash numbers did tick up a little bit. Fatal and serious injury crashes, and then fatal and all injury crashes did decrease a bit at the J-turns for commercial vehicles when we put them in. Again, we're talking small numbers. None of these were statistically significant, but no major red flags, I would say, when we talk about commercial vehicles at these locations. We did see an increase in single vehicle crashes, mostly not associated actually with the intersection. The J-turn does have a wide envelope that we're looking at from U-turn to U-turn, so looking at all the crashes that happened between those two U-turns. But a couple of the crashes were related to the J-turn, and two of them were actually related to vehicles failing to navigate the U-turn properly. And we also saw an increase in rear end crashes, kind of like what we saw in general when it comes to commercial vehicles. There was a previous study done a number of years ago by MnDOT that looked at operationally J-turns for commercial vehicles, and it found that queue times, the queue time, how long a vehicle is waiting before it starts to move through the intersection, is similar at a J-turn, because again, you're dealing with one direction of mainline traffic at a time. So you have shorter queues, but there is, again, that added travel distance. So getting through the intersection as a whole does take longer at a J-turn for commercial vehicles. But again, we're seeing those good safety results. So more to read through in the report if you want to. That's all I'm going to share here. If you have any questions, send them my way. Otherwise, I think we're holding questions here for the end, so we'll do all three presentations. So I will pass it on to Dr. Imran next.
Dr. Hay, I think you are muted.
Sorry about that. Thank you, Max, and thank you, Julie, for reminding me and also initial introduction. I hope you can see my screen now.
Yes.
Okay, wonderful. So this part of the webinar is a presentation on an app which we have developed over the last few years, Unintentional Lane Departure Warning app using GPS technology. Um, so I'll give a brief background and project overview, and then app development, its functionality and scope, and then app demonstration. I have a video for the app demonstration, and then, of course, questions can be taken at the end. Uh, so, so sometimes when a driver is under, a tired, drowsy, or maybe sometimes under influence, uh, they are kind of, going on a straight road, especially on a freeway. They can swerve the steering a little bit, and they they get out of the lane. There are solutions which exist, like rumble strip is very common, which only works on the extreme end of the lane. There are camera-based systems on many vehicles these days, especially a little bit higher end trims, which basically take pictures of roads frame by frame by frame. They compare, and whether they depend upon the lane markings on the roads. So they compare frame by frame and see if the vehicle is moving out of the lane without turning on the indicator signal. So if that happens, they are warned. But the problem with that is that sometimes if the road is snow covered, our lane marking is worn out, they don't work. So we wanted to do this using GPS technology. So the idea was, the concept is in the upper row, that GPS technology basically can record the trajectory of the vehicle. From that, if we do some processing and can estimate if the lateral departure has occurred. That was the idea. And then we developed the proof of concept, developed the algorithm, and did the proof of concept using a Safari device, which had a built-in GPS and an onboard computer to process that trajectory. And then we used the regular computer, for the warning signal. And the next step was to develop an app, or accommodate those algorithms in a navigational device. So we chose the app option. So now we have developed the app, which has some limitations, which I'll talk about under the scope part. So that's the whole project overview. It's a few years it took us to reach to that level. This is just a basic example of what do I mean by lane departure warning, using our lateral distance estimate using the trajectory. You can see this is the red line is basically the GPS points, acquired GPS trajectory of a vehicle moving on a road. And you can see that, from a straight line, intentionally from left to right, vehicle went and then came back to the lane, and you can see the lateral distance, peak distance in the middle is about 2 meters. So that can be estimated using the algorithms which we develop, very simple algorithms which we develop. So you can see that this is the vehicle on a lane, and then the dashed and dotted gray line in the middle is called the reference direction, reference heading of the road. And then the blue dotted line is the trajectory of the road acquired by GPS. So each dot is a GPS points. So we compare the direction of the vehicle with the reference heading, and the differential angle can get us the lateral distance, and we keep on accumulating the lateral distance. And when lateral distance increases a certain threshold, which we estimate to be 1 meter, because a typical vehicle width, a typical lane width could be 3 to 3.5 meters, and 2 meters are roughly the vehicle width. So there is about a meter on each way. Although even though vehicle is not traveling in the middle, but we are estimating about 1 meter lateral distance without giving indicator signal will be considered lane departure. So you can see here it is depicted better. The cumulative distance versus travel distance is shown on the lower curve, and the vehicle takes a lane departure from right to left lane and then comes back to right lane, and you can see the lateral distance increases in one direction and then increases in the other direction. So when lateral distance stops accumulating further, the slope becomes zero. We snap it to zero again, the cumulative lateral distance, so that we are ready to detect the next lane departure, which could be in the other direction. This is, by the way, intentional lane departure, but it's in principle, this can be used for unintentional lane departure as well. So the way we do is basically we need a reference heading of the road. Initially, we did this way that we wanted to use a prior trajectory of a vehicle as a reference heading, so that we can predict future lane departures. So for that purpose, a vehicle needed to travel on that road at least once before, so that we can implement our algorithm. Uh, this is how it works. Any trajectory, a prior trajectory, consists of either a straight section or a curved section. And in between straight and curved section, there's a transition section. So our algorithm, basically, this is a second algorithm which we developed to convert the trajectory of a vehicle into a road reference heading. So our algorithm splits that depending upon the heading and differential heading of the trajectory. Based upon this, we convert that into three sections: straight, transition, and curve sections, any trajectory. So later on, we realized that we could also use Google trajectory, like Google Maps. This is a Google Map example, that we could convert that. We could use that as a trajectory and can convert that into straight, transition, and curve sections. So we developed a backend browser tool, RRH generation, road reference heading generation tool, which can either take the prior trajectory, past trajectory of a vehicle, or a Google trajectory, to convert that into RRH. So once we have RRH, we could actually implement our algorithm. So here is the design implementation plan for the backend browser. You can see either a Google route or a past trajectory can be used to convert to RRH, and this can be, this can reside in a database, and LDD algorithm is in the backend browser just for testing purposes, but mainly it's in the smartphone app. So any road where you're going, RRH of the reference, a particular road can be extracted from the database, and then GPS can give the trajectory, and based upon that, LDD algorithm can convert that to a warning signal. Right now, we are using audible warning signal. And this is the smartphone app and smartphone and backend browser interaction. You can see a secure connection needs to be established, and then RRH extraction and retrieval tool, and the past trajectory upload is also facilitated here. So either Google route or a past trajectory, a database. This is more like a database detail. It's not necessarily important for this purpose. So I'll straight go to the app functionality. You can see the left-hand picture is once you open the app, you register with your email and password. You allow the use of GPS as a standard. And then you can see the third picture this is how the app looks like when you open first time or later on as well. And this is just the phone, Android phone, open app picture. You can say start and pick a file. Right now we have manual pick a file, means you pick the road reference of a particular road to make it work, because this is not a commercially available app yet. And one of the main reason, I'll tell you shortly that why is that. So this is that reason, the scope of the apps, the qualification. I want to qualify what we have developed. You can see, so there's a GPS device in the middle picture along with the phone. We were not able to use the phone GPS. The reason is that both Android and Apple iOS has restricted the use of GPS at high frequency. We need GPS to work at least 10 hertz, which both phones GPS are capable of doing that. Any GPS is capable of doing that, but just to save the battery life, iOS and Android platform, they have restricted the use of GPS beyond 1 hertz frequency. So that's not good enough for our application. So we use these external GPS device to get the data, because we tried our best to tinker with the iOS and the Android platform. We couldn't work. But it's not a fundamental problem. Uh, if Google Maps or iOS, Apple agree to make this part of their feature, this app as a feature of their maps, this they can unrestrict that. But for now, we are using an external GPS device, and you can see the difference. I'm going to, sorry, actually, let me put that in presentation mode, then it will work. So you can see the left-hand picture. This is using the phone GPS 21, 22, 23. So every second you are being updated. But on the other hand, the right-hand side picture, you can see there are 10 points per second. So this is the external device. So that's the reason we right now are only able to develop for Android app, although the software which we have written, it's applicable to iOS as well. But because the external GPS is hard to make work, we were not able to make the external GPS work with the Apple phones yet. So this is why it's only available for Android phone, and we need an external device, GPS device, to make it work. So that's, I wanted to qualify that. And then now let me give you the demonstration. This is the demonstration route. This is I-35 near Duluth. So point A and B. So this is basically Google Map. It's about, I think, 5 miles or so distance, or maybe even 10 miles. So this is the demonstration setup. You can see the middle phone is just to record the road, so you can see the lane marking, a lane when the lane is changed left or right. You are able to see that in the video of this camera, the middle camera. The right phone actually is running the app that will be able to tell us whether the lane has been deported or not. So you can see these are the two videos. They are synchronized. The left is the camera, so where you will be able to see whether the lane has been turned left or right. And then right side, you can see the Google Map. So these location signs are just may change color depending upon whether this is a straight section, curve section, or a transition section. You will see they will keep changing colors, but mainly the red blue dot, the bigger one is actually vehicle. The smaller one is the Google Map one, but the bigger one is our dot to show the vehicle. This will change color, as well as there will be a sound when the lane is being changed. You should be able to see when I run this video. This is, I think, couple of minutes video, so I might run only for first minute or so, where you'll be able to see a few lane changes, and you'll be able to hear the audible warning, as well as the blue dot will change to red. So you can see that how, let me go back. So you can see, this is a little bit longer video covering entire about 10 miles or so. One advantage of covering the whole section and making the video was that we wanted to show that there are no false alarms. Actually, in the beginning, we had quite a few false alarms. We still see once in a while there's a blip, a beep, when there is actually no lane change, but the algorithm assumes that there's a lane change, uh, but that's only for a very brief period of time. But you can clearly see that as the lane is being changed, each lane is being detected successfully. Of course, this was intentional lane change and indicator signal was on, but basically this can work if this is somehow integrated in the phone or in the dashboard of the vehicle. The indicator signals can be used to detect if it is unintentional or intentional lane change. And I think that's about it. And I believe the questions can be taken at the end. Thank you. And I think I'll hand over to Hannah now.
Okay, good morning. If anyone was asleep during that part of the presentation, they certainly woke up with that first alarm. Holy cow. Okay. So, okay, great. I am going to talk through a research project that we finished a couple years ago. We started it in 2020, and so we had, COVID-related challenges getting going. But this is something that I'm very interested in. I was a technical liaison for this project with the University of Minnesota. So the scope of this study, we're going to talk about drivers yielding to pedestrians in a certain subset of conditions. All of our study locations were unsignalized intersections, so there are no traffic signals, there's no walk sign or green light. They're not mid-block locations, so they are at intersections. And in the interest of time, I will just tell you that the pedestrians who are crossing or waiting are performing a legal maneuver and have the right of way. We talked a lot about crosswalk law and that kind of thing as we got started here. And then one thing that I just want to emphasize, which I think anybody who's doing research will tell you, I'm going to show you some correlations. That is not the same as causation. So I'm going to show you some situations where two things exist in the same place at the same time. It doesn't necessarily mean that one of those things is causing the other thing. So to sort of oversimplify the pedestrian vehicle interaction, there's three possible outcomes. Either the pedestrian yields to the driver, or the driver yields to the pedestrian, or unfortunately neither happens, which is obviously the thing that we're trying to avoid. So the objective of the research was to identify factors at a given intersection that result in improvement in driver yielding to pedestrians. Some of the side factors are things that we can potentially control, like the geometry of the intersection, signs and markings. Some of the other things are out of our control, like weather, which is still very informative to know what's going on. And most importantly, some are indirectly controlled by our engineering decisions, including vehicle speeds. So for this project, we did data collection at 18 sites in Minnesota. Most of them were in the Twin Cities, a couple of sites outside the Twin Cities. First, we kind of looked at, just did some digital scoping of the locations. You can see here a picture of the equipment. Those are actually several car batteries running the camera at the top of the pole. So we need a good place to secure that. This setup is from several years ago. I think the U has gone to something that's maybe a little bit less heavy, but the car batteries actually are great because they were able to take 2 weeks of continuous data, which is something that a GoPro or something like that usually is only about 48 hours. So that was really useful, being able to collect a long period of information. So our data collection sites tried to represent some various features that were identified in the lit review. Most of the data collection occurred in the summer of 2021. We did do a pilot where we collected data at a couple of locations. So I think we've got 3, Minneapolis, Richfield, and St. Paul, that we did in 2020 just to sort of test the process before spending all the energy to put the cameras out at all of these different locations. So one of the classic issues with pedestrian data collection is that we needed a lot of interactions between pedestrians and drivers in order to do the analysis. But we need to have, in order to do that, we need to have locations where people are willing to cross, which means it has to be somewhere where they're comfortable walking in the first place, somewhere with gaps in traffic so that people have a chance to cross. Because remember, we're not at signalized intersections. These are all locations where pedestrians need to assert their right of way in order to get across the street. And that means that we have to do sites where drivers are going 40 miles an hour or less, which is interesting because, you know, we spend a lot of time talking about how pedestrians should can be able to cross higher speed locations. So intersections where the speed on the roadway is more than 40 miles an hour. But the problem that we had with respect to this research is that the pedestrian is going to have to look really far down the road if someone is going 50 miles an hour or more in order to be able to see and judge the gap. And as a result, it's sort of the circular thing where not a lot of people try to walk at those intersections. So most of our locations are in more urban areas. We have a couple of more suburban areas where the speed limits were a little bit lower. I have a video here. This video does not have sound, so no alarms here, but I just wanted to show you, this is what the images look like. We had a grad student from the U watch the video to look for pedestrians and cars interacting. So there is someone waiting to cross this street across here. You probably won't notice them until they step out. Oh, there they are. Kind of waiting by that sign there. So it looks like the far side driver actually yielded to them before the near side driver. But there were several drivers that passed through the intersection, you know, prior to the pedestrian stepping out. So one of the things that is okay, so here are the features that we collected. So some of those are you know, one-time things. The posted speed limit is what it is. But then you know, the type of the pedestrian, the size of the group, the speed of the vehicle, all that stuff was specific to the interaction. We spent a long time on this list and we could have collected a lot more things, but we needed to try to rein in the scope to the best of our ability here. We found that driver yielding to pedestrians varied greatly between the sites. So we had 2 high yielding locations, Cleveland and Pinehurst, which was the one that I just showed you in St. Paul, and 52nd in France and Edina. What's really interesting is the relationship between the total number of interactions at the site and the amount of yielding. It is not any sort of linear relationship, but you know, our 2 sites with the lowest amount of yielding had some of the fewest interactions. And so, you know, perhaps drivers are not accustomed to encountering pedestrians in those locations and then don't even notice them. That's my conjecture. So then very basic summary statistics for some of the information that we collected. Vehicle speed was the most significant factor in predicting whether or not a driver would yield to a pedestrian. So the average driver yielding rate went down significantly, over 25 miles an hour, which is not very fast. So I think we were definitely correct in not attempting to collect data at sites with more than 40 mile an hour posted speed limits, because I think that we would just get a bunch of zeros. Some of the other basic summary statistics. So drivers were more likely to yield at a crosswalk with a sign than without a sign. And they were more likely to yield at crosswalks with markings versus not marked. So, you know, good news for the traffic engineering community. It turns out that putting our signs and pavement markings out there can have an impact on how drivers behave. All right, so I mentioned we had humans processing the video. I know there's a lot of interest in trying to automate that kind of thing, but we weren't there yet. And actually, it turned out really interesting because one of the things that we didn't identify until we started looking at the video was the different types of yielding that drivers might do. So sometimes they come to a complete stop to allow the pedestrian to cross. Sometimes they might not come to a complete stop, but slow down enough so that, you know, the person can get through the intersection, and then changing lanes to avoid a pedestrian, which isn't really a type of yielding, but is something that happened often enough that we needed a category for it, or just not yielding at all. Then for pedestrians, we found a couple of different behaviors as well. So I wonder if you can see yourself in one of these groups: crossing at a comfortable pace as soon as you see a gap, crossing quickly to use a small gap, waiting after the gap was present before crossing at a regular pace, waiting and then crossing quickly, or not waiting at all and just going for it, asserting your legal right of way to cross the street. I think when I was younger, I was probably more in that last category. And I think I'm more of a wait for the gap, wait after the gap kind of person at this point. The size of the group of pedestrians was also significant. So if you have a street that you're having trouble crossing, consider bringing some friends with you. Yield rates for one pedestrian, on average about 37%, but with 5 pedestrians, you're up to 70%. So I think people in cars are more likely to notice a larger group of people. We watched that video with one person standing next to a sign. If there'd been 6 people on that corner, maybe we could have noticed them sooner. I am not an academic, not a researcher, but we did do statistics here. So the odds of a driver yielding are lower with each unit of speed increase. So every mile an hour that a driver is going faster, there is a percentage reduction in the probability that they will yield to pedestrians. So I showed you that just the frequency exhibit before, but this is the attempt to predict what will happen. And, you know, I can definitely see a case to be made for 20 and 25 mile an hour speed limits in high pedestrian areas, because anything over about 24, 25, and the odds that the pedestrian will be yielding to the driver go way, way up, which is sort of the inverse of the driver yielding to the pedestrian. So we did find some site variables that were significant. So I mentioned good news about signs and markings. Other stuff was a little bit harder to parse. So, you know, number of lanes had a negative impact on driver yielding. That makes sense. Bike lanes also had a negative impact on driver yielding. Unclear what exactly that that correlation is about. And then bus stops, actually, some positive yielding there. So our 2 biggest findings were signs and markings, but, you know, trying to capture all of the things that happen was a little more challenging. So I've already mentioned it, but I'll say it again. Vehicle operating speed is the most important predictor of driver yielding. Other important predictors are the land use context and distance to common pedestrian destinations. Pedestrians tend to wait for a sufficient gap to arise. So, you know, sometimes when we're trying to figure out what to do about pedestrian safety, we say, well, we should, you know, tell people to look both ways before crossing. Let's have an information campaign about that. But generally speaking, from watching these videos, it looks like folks definitely are aware that they are entering a dangerous situation and tend to wait to be certain that they can cross. And we were able to accurately predict driver yielding with some of the identified features. So, of course, now the biggest question is, how can we effectively reduce the speed of the vehicles in contexts where we want drivers to yield, you know, especially in those locations around schools or parks or business districts or, apartment buildings, all that kind of stuff. What can we do to get drivers to slow down so that then they are in a position to yield to pedestrians? So that's probably the biggest question in my career. Anyway, so that's it for me. I will stop sharing my screen here. Looks like we've got a couple minutes for questions. So.
Yeah, thank you to our presenters. Thank you, Hannah, and to our other presenters. We do have some time for questions, and we've got a few things in the chat. If you'd like to ask a question, please put it in the chat, or you can also raise your hand, and we will. And make sure you're unmuted, and you can ask a question that way. So I'm going to go back to the chat here, and some of the questions have been answered, but I think it would be great to answer them to the whole group. The first couple are for Max, and the first question from Stephanie Smith is, were you able to verify if the right turn to main line is consistent with the volume increase of that movement?
Yeah, so we saw, as mentioned, we saw crashes increase for those right vehicles turning right onto the main line at the J turns, and volumes increased. I did not have turning movement counts at all these intersections before and after, so I can't definitively say it's exactly tied to the volume. If I had to guess, I'd say it probably is an increase greater than the volume, just based on the numbers we're seeing. So there are more right turn crashes, whether that's due to maybe the channelization or longer queues, or just driver perception of wanting to get through there faster. I can't exactly say, but we are seeing more right turn crashes. Some of those have been injury crashes, but a lot of those tend to be lower severity. But obviously, we don't want to see any increase in crashes. So something to be aware of when you're looking at your putting in the J turn.
Thank you. And I'm going to follow up with another question for Max from Brian Tang. Given the benefits of allowing right turns directly into the median U-turn decile lane, why not also allow left turns, U-turns directly into the right turn decile lane from the median? Shouldn't that have similar benefits?
Yeah, so with most of the J turns going in now, the deceleration lane for the U-turn lane goes all the way back to the intersection. So if you're on the minor road, you can pop right into that turn lane instead of having to turn onto main line and then merge over into that turn lane. And we did an evaluation. As part of our evaluation, we looked at the intersections that had those U-turn lanes pulled all the way back to the intersection against the J-turns that did not have it pulled all the way back. And we didn't really see much difference in the crash rates and the changes in crash rates. So even though I personally like those turn lanes pulled all the way back, the data didn't bear out that they're way better. So kind of on the converse, when you're coming out of the U-turn lane, the right turn lane, if that was pulled all the way back, you could pop right from the U-turn lane to that right turn lane. Typically, you're merging onto main line and then turning right onto the U-turn lane. So if the same theory holds, I don't know if we would see a huge difference in crashes if we're pulling it all the way back. And we haven't seen a ton of crashes either from people coming out of the U-turn lane.
I'm going to jump in just to mention that having the decel lane for the U-turn after the intersection makes the design of, if you have a pedestrian crossing through your J-turn, makes the design of that pedestrian crossing a little bit easier because then they're not having to cross that decel lane. So if it's, neutral with respect to crashes, but gives us a design benefit, then probably why we're doing it.
But Hannah,
Thanks.
I said I prefer it as a driver. Doesn't that
as
hold
you
any weight?
No, totally, absolutely. Your anecdote is what we should go with. Yeah.
Following up with a question for Hannah from Stephanie Smith. It's great to get observational correlation data on a large number of Minnesota pedestrian crossings. I'm curious what's next for research in this area, additional study of same intersections next year for confirmation?
I would love to do that. I think Julie mentioned at the top how many research proposals there are and how many get funded and that kind of thing. So our office has pivoted a little bit into some different stuff. We're working on grade separation for ped and bike crossings right now, and then some bicyclist operating characteristics. But I mean, as we're doing this, I would love to add more sites. I would love to go back and look at the sites we previously did, see what kind of changes we can get over time. Obviously, if you ask any researcher if they would like more data, they'll always say yes. Yeah, so I don't have anything specific to pedestrian crossings in the pipeline right now. But it's, something we're always talking about. So.
Thank you. A question for Max from Michelle McGowan. J-turns have been used in Michigan for 40 plus years. Glad to see they're being used elsewhere. Most people get confused with the Michigan left.
Yeah. So I agree. It's glad to see that we've kind of taken that slightly different than the Michigan left, as Michelle kind of noted, where on those, sometimes they're signalizing you can go through, but if you want to make that left turn movement, you've got to make that right and that U-turn. And for some reason, people in Michigan obey that, which is wild to me that they don't turn left there. But I guess maybe we don't trust our drivers as much, so we force them to make that right turn. Slightly different design, but yeah.
A question for Professor Hay, from Molly Yang. Who is the intended audience for the app, and what are the next steps for implementation?
So it is supposed to be for anybody, public use. However, I think the next step will make it happen. We are working with to approach Google and navigation like TomTom and Garmin, as well as Apple, to see if they are willing to make this part of their device feature, our Google Maps feature, or say TomTom navigation device feature. If that can happen, actually the the vehicle signals can be used to distinguish between unintentional and intentional lane departure, and that can be more useful for everybody. So effectively, those vehicles which are older and do not have any lane departure warning system in them, they could potentially use this app, although the turn signal will not be active. So the turn signal will not be integrated in the smartphone app. So that what they have to distinguish themselves, but it can still be a safety feature for them.
Thank you. We're at 11, and I'm going to ask one more question. It's a follow-up for Hannah. And it's from Stephanie Smith. Also, did the yield speed correlation have a similar result on posted speed versus actual speeds traveled? Curious if drivers are going slower because they anticipate seeing pedestrians at a heavy ped volume intersection.
And I was just typing out my answer because I wasn't sure if we would have time. So the correlation that we saw, we got actual driver speeds as opposed to posted speeds. And so that correlation is like per individual interaction. So people who are going more slowly are more likely to yield. Whether or not they're going more slowly because they expect pedestrians is a really good question. I don't know. I mean, I would hope so. Ideally, all of the drivers would expect pedestrians and then drive more slowly and then yield to them, right? That's sort of like the perfect world that we're trying to build. So maybe not a comprehensive answer to that question, but definitely something that we were thinking about as we worked on the project.
Thanks. And again, I want to thank our presenters today for a really interesting webinar. We are going to send out an email to you all with a link to the recording of this webinar and to the projects that they've discussed today and some other information from our office. We hope you'll join us for our Research Radar webinars in the future. And we want to thank you all for joining us. This does end our webinar today. Bye, everybody.
Thank you.
Thank you.